Hi, I'm Cameron. I'll be introducing you to a paper and architecture called MAMBA. The obvious image here is the black mamba, and if you research this on your own, you'll see everybody using the snake in their thumbnails. But where my mind first went to is the candy called MAMBA, so I just kind of put them both on here, and maybe the snake is eating the candy. Anyways, MAMBA is an architecture specifically designed for language modeling. It's a development on a framework called state-space models, specifically the state-space model called S4, and the state-space models themselves are kind of an improvement to RNNs. You can kind of think of this as an outline for this presentation. I think a really nice way of viewing this setup here is that there's this trade-off between efficiency and capability when it comes to language modeling. And RNNs and transformers sit at opposite ends of that trade-off. RNNs are really bad at NLP, but they're very efficient when it comes to scaling input size. Transformers are very good at NLP, among other things, but they have very poor scaling. There's another factor at play, which is transformers can be trained in parallel and RNNs can't be parallelized. So MAMBA sits not between the two extremes, but actually gets the best of both worlds. Scales much better than Transformers and it's very performant. Actually more capable than Transformers at language modeling. So this is a breakdown of that. The key takeaways are that inference is much faster, training is easier, and perplexity is lowered. So that's what this is here on the bottom. Here MAMBA is in purple. Now's a good time to mention I'll be glossing over a lot of the specific detail of this paper in favor of a hopefully more motivated conceptual understanding. So maybe those graphs didn't look too impressive to you, but MAMBA caused quite a stir in the community when it was first released. It was submitted to ICLR last year, but was available in preprint and on GitHub since 2023. Several people and teams had replicated and verified the results, and everyone expected a complete paradigm shift away from transformers. So it came as a big surprise when it was then rejected from ICLR. More than the fact that it was rejected, the reasons why became a bit of a controversy, and the situation is often referred to in the community as the MAMBA drama. So you can read the official reviews on Open Review, and all but one reviewer recommended the paper be accepted. Here's what they had to say. Among other things, their main issue was that MAMBA wasn't tested on a benchmark called Long Range Arena. So for context, Long Range Arena is not a language modeling benchmark. And remember, MAMBA was created as a language model. So it seems kind of strange to expect this sort of benchmark in this paper, and even more strange to reject the paper entirely for not including it. I've cut some of these screenshots for brevity, but another point of contention seems to be a misunderstanding on the reviewer's part, not only on how MAMBA works, but on how transformers work as well. So if you happen to be this anonymous reviewer, hopefully I can help shed some light on things in this presentation. Back to transformers for a second. I'm sure many of you have noticed that no paradigm shift occurred. Transformers are everywhere, and it doesn't look like they're going away anytime soon. This is Chatbot Arena on Hugging Face. These chatbots are subjectively evaluated by thousands of people, and that's where this graph comes from. As you can see, it's transformers all the way down. There's a reason that transformers are so ubiquitous, and that's because the attention mechanism is very powerful. However, transformers struggle with long sequences. I thought it worth mentioning that there have been some recent improvements in regard to transformers performing well for long sequences. This is Fiction Livebench. They give models long stories and then quiz them on details of the stories after the fact. I can't say for sure what sort of trick Gemini 2.5 and O3 have up their sleeves since these models are proprietary, but it seems likely that these are just hardware tricks. Transformers, at their core, still have this scaling issue. And that's because they need to compare every token with every token. I want you to imagine reading a book and stopping at every new word to start the book over again and compare it to every previously seen word. Morally, that's what a transformer is doing every time it parses text. So there's these parallel scaling problems in performance, but also in computation costs. I put this chart here in case you're not familiar with Big O notation. The idea is that if you want to apply a neural network to a long-range task, especially one with potentially unbounded context length, like language modeling, it generally wouldn't be a good idea to use a transformer unless you had the hardware to scale up implementation in return. There's some tricks you can pull, but transformers still have this scaling issue. Fixing the scaling problem has been a point of focus for quite some time, and there have been a lot of proposed fixes in the past. I want to focus your attention on RNNs for now, but I also want you to make note of some of these other ones because they'll come back up later. The advantage RNNs have is they scale conservatively with sequence length. Not only that, but because it's one input at a time, RNNs have a theoretically infinite context length. One of the new issues this presents, though, is losing out on contextual information too far in the past. This is the vanishing gradient problem. Structured state-space models actually have a pretty far-reaching theoretical background, but they happen to solve this issue. I'll take a bit of a detour to explain how they work, but where we're at right now is that efficiency is better than with transformers, but you're not going to be using these things for language modeling just yet. The reason they don't suffer the vanishing gradient problem is because there's no nonlinear activation function constantly shrinking your gradient. It's replaced with this new state update function expressed by the linear combination of the previous state, and the current input. What this gives you is an ordinary differential equation describing movement between states. So I'll back up for a second and explain some of that. First of all, what are states? What should you think of when I say the word state? The states are where the context comes from. There's some sort of learned compression of everything that the model has seen in the past. Each state is a latent space that encodes the core details of the environment. In the context of language modeling, for example, your states will be vectors that encode abstract learned concepts like negativity or sophistication. When I say that the update between states is modeled with a differential equation, what that means is that you can predict what the next state will be if you know certain details about the current rate of change of the state through state space. If you're not familiar with differential equations, that may take a second to get used to. As an analogy, I've pulled this from the 3-1 Brown video illustrating the movement of a pendulum through the different states that a pendulum can be in this case defined entirely by its angle and momentum, which is the rate of change of the angle. Drawing these phase spaces is a common trick to get an intuition for how things generally behave when their behavior is described with a differential equation. You can imagine a state space model moving through the state space vector field as it updates its state according to what the previous state was and according to the current input. That input defines how the model deviates from its natural path. In the second part of this animation, that's shown as this air resistance term, which alters the shape of the vector field. This other equation just tells you that the output at each state is proportional to the current state undergoing some linear transformation defined by this matrix C. State at time step 0, input, output, state at time step 1, input, output, etc. For now, we're focusing on a specific state space model called S4, structured state space for sequence modeling. There's 4 S's, so S4. The difference with S4 is there's specific handling of long-range dependencies with something called Hippo, which I won't get into. Unlike pure differential equations, we'll need to have the movement through state space discretized in order to run it on a machine. This can be done recurrently, as we've already seen, but there's a duality between this approach and a convolutional method. I'll go through the equivalence briefly. Here's the graphic from earlier. If you want to define your outputs in terms of your inputs instead of just your state, you can add each of the paths from input to output. So bear with me. Output at time step 0, C, B, X0. Output at time step 2, C, A, B, X0 plus C, B, X1. Output at time step 2, C, A, B, X0 plus C, A, B, X1 plus C, B, X2. As it turns out, this is equivalent to doing a one-dimensional convolution over your inputs, where your kernel is the maximal expansion of your matrix coefficients. Reverse it and slide it over your inputs and you get the same set of equations. So you can imagine S4 as a combination between an RNN and a CNN. The advantage here is that convolution is very parallelizable, and there's a lot of tricks to handle very fast convolution, whereas RNNs have very fast inference, as I mentioned earlier. So you can do this CNN computation during training and this RNN computation during inferencing. There's still one issue, which is that SSMs as I've described them are what's called linear time invariant, which means that the parameters of the model don't change given different states or inputs. This means that they can't adapt their behavior based on the content of the input, so they treat every token the same. For language, you can imagine maybe you're parsing a speech and you're giving equal weight to every utterance, critical context as well as filler like or We need some way to select important information to remember and irrelevant information to ignore. This is an example from the paper of a task that a linear time invariant model can't complete. I'll gloss over it, but the idea is that it can't distinguish between filler whitespace and task relevant information, which is these colors that it's trying to copy over. The main thing that MAMBA does is make it so that SSMs can be selective. This is done by making the dimensions of this B matrix input dependent. The B matrix from earlier maps the input to the input component of the state update vector. It's now defined as the hidden dimension by the length of the input by the batch size, instead of being fixed like it was before. The connection here is that this is very similar to gating mechanisms like those found in LSTM models. It's also sort of like the transformer attention mechanism. It's a different process, but it accomplishes the same thing, this input selectivity. MAMBA also introduces a hardware-aware algorithm for more memory-efficient training, which I'll explain in a bit. Here's the MAMBA architecture described as a combination of this gating mechanism I mentioned and the classic state space model architecture called H3. The state space module in MAMBA is called the selective scan structured state space for sequence modeling, so now we're up to 6 S's, so S6. The other thing here is that the intermediate vector size is scaled up quite a bit before being scaled down again. They're scaled up so you can fit more information in the state, and the reason they can do this is because the real bottleneck here is transfer time to the GPU. So once it's there, you can scale up for more computation cost, but that was never the bottleneck. You have to transfer the vector anyway, so you get more context information essentially for free. I have a bit to say on the hardware-aware algorithm. The idea is that there's speed costs when it comes to transferring between the two types of memory in the GPU. So they fold the state update and discretization to one calculation using one memory. The connection here is with flash attention and transformers. So to wrap up, MAMBA not only scales better than transformers, but is better at language modeling. They just haven't gotten much attention within the ecosystem. I wanted to make one more comparison here, which relates to how these different architectures compress context. You can imagine that transformers do little to no compression, depending on the implementation, since they're more or less caching their entire history, whereas RNNs have very strong compression. You have to get all of the previous context to fit within a certain fixed length vector before passing it on to the next time step. You can see MAMBA as a compromise in this regard since it selectively compresses context depending on the input. Since you're now familiar with the naming convention, I wanted to briefly return to the long-range arena benchmark to show you that state-space models had already performed better than transformers at the time of this paper's release. As far as I'm aware, MAMBA still hasn't been tested on this benchmark, but it makes you think. Speaking of naming conventions, it seems like every series of models has to have their gimmick, whether it's Bert, Bernie, and Big Bird, or Llama, Alpaca, and Guanaco. In this case, the gimmick is to replace the first letter of the word Mamba, so you have follow-up models like Jamba, Zamba, and Samba. And while it seems like very few people are interested in testing and scaling Mamba architectures, I did find Jamba sitting at number 73 on the chatbot arena from earlier. The other thing to mention is that hybrid Mamba transformer models seem to be uniquely performant for some reason. The authors of the paper did a talk at the conference on language modeling last year, and they shared some cool graphics I thought I'd show you. This first one is a breakdown of the domains that MAMBA applications have been applied to within a few months after being released. So it was designed for natural language processing, but it seems to have good out-of-the-box capability across many other domains as well. The other one is some large implementations and related models along with their parameter count, just to give you an idea of the state of implementation as of late last year. That's all I had for you. Sorry I wasn't able to present this to you in person, but if you had any questions you wanted to follow up with me on, this is my school email. Feel free to ask.